did bachelor's degree work in Serbia in electrical engineering, and then he went to the University of Belgrade to do a master's also in EE. And then he came here to the U.S. and did his PhD work at Temple University, and then did a postdoc in bioinformatics at IU School of Medicine, and then joined the faculty here and has been in the School of Informatics at the university. So let's welcome Pedja. Thanks so much.
Thank you. Well, thanks a lot. This is a great audience, and I hope you're at least a little bit enthusiastic. This will diminish, I promise you, by the end, but hopefully there will be some useful material that will intrigue you at least to some level. So most of this work, and I want to start with the thanks because I may not finish the talk, but it has been conducted with Shantanu Jain, Martha White, and Michael Trosset, and I think they're all here. So if you need any details, they actually know all of that and probably more than I do. It's been really fun working with all of them on this project. But I'd like to start with some motivation for estimation of proportions, and I'm going to start with a friend of mine, Matt Hahn, who last summer sent me an email, which was a tweet. I'm not on Twitter, so I rely on people sending me email retweets, so to say. So it was in the middle of July, and it says that 1/3 of the alternative splicing isoforms produce functional proteins by a person who is actually relatively known in the field. At least that's my understanding. I checked him. And this was important because we just had a paper accepted on a similar topic around that time, and we care about what proteins do and functional proteins. So it was an interesting thing, and I felt, oh, these people did some work, and this is a very interesting result. So I actually went to this paper and I wanted to check it. And my first surprise was that it's actually semi-supervised learning predicts approximately 1/3 of alternative splicing isoforms as functional proteins. So that's still interesting, and it still may be correct. But I care about this because using predictors to make these types of estimation of proportions of something, for example, what fractional proteins do something, is an interesting problem. And so I take a look at the paper, and here's a paragraph, and then I get even more surprised. It says at a 90% true positive rate, we predict that about 32% of isoforms are functional, roughly consistent with one school of thought, which estimate around 20 to 30%. So now that's an interesting statement because they say at a 90% true positive rate. So there's some threshold that's been involved in this situation. And then the question is, why not 100%? Why not get them all? So how do we decide that it should be 90%? That led me to read the supplement of this paper with this, because all the methods are in the supplement. Turns out they actually know how difficult this problem is. And the problem is difficult because we have a set of proteins for which we know they're functional, and we have another set of proteins for which we don't know what happens. We just predict they might be actually proteins, maybe they're functional, maybe not. So we think of it as positive data and unlabeled data, right? We don't have any proof that something is not functional. And they used proper methodology, but in the end, if you read the paper carefully, they actually don't say what they did. So this might be a correct finding or might be incorrect finding. So just before I move to a regular talk, I'd like to update this tweet. So it should be, at some prediction threshold, 1/3 of alternative splicing isoform is predicted to produce functional proteins. But there's much more of that. And this is a particular paper that intrigued me back in 2002. It was written in 1999 when I worked in protein phosphorylation. This is a modification, chemical modification of proteins, when this group from Denmark predicted that they estimated fraction of phosphoproteins, so this is some particular type of proteins, might be as high as 30 to 50%. And they used the predictor to actually do that. Well, a few years later, here's another paper that says at least 30% of proteins, these are not necessarily inconsistent, but of these proteins are phosphorylated, which says, and there's other actual works that some of the people they don't have methodology behind, but they say maybe all proteins are phosphorylated. So which is it? Is it 30 to 50%? Is it at least 30%? Is it 100%? How do we know? And even if you look at human genome paper that was published in 2001, they sequenced the human genome, and they found out that at that time they had predicted that there's 30 to 40,000 human genes. And they say that. There's 30 to 40,000 human genes, roughly 50% more than in fly. And it turns out later that it's actually, there's only 20,000 human genes by now, we know, and it's roughly the same as in fly. So how can we make those mistakes in all these problems by so much? This is the point that I'd like to make. And so I have my own point of interest in here, and it's also a very simple question. Because we care about protein function, we are interested just to know, for example, how many of these proteins, what is the fraction of these proteins that are enzymes. So enzymes are proteins that catalyze reactions. So if you eat something, your enzymes in your stomach are going to degrade the food that you eat, basically. So that's one sort of enzymes. There's many different types of enzymes. So when we worked on another paper in 2010, we knew at that time from a database, which is a kind of consortium between Europe and USA, that about 28% of proteins that at that time were known to be enzymes. So of all proteins that we knew function, 28% were enzymes. And at that time, I thought, oh, about 1/3 of proteins are enzymes. Well, last year, I was really surprised when we recalculated this, and it turns out now there's 40%. So what does that mean? Do people only work on enzymes, or actually there's maybe different distribution of proteins started entering, and which numbers should be correct? Right, so can we use machine learning to actually predict or somehow estimate the fraction of enzymes either in a particular genome or overall? I think it would be interesting. And then there's many more, actually more complex questions. This is a toy real question. So I looked at different organisms. E. coli, it has about 4,500 genes. Currently, we already know that 26% are enzymes. So that's a known result. They've been shown in a lab, the enzymes for sure. But for the rest of the proteins, we don't know. E. coli is a bacterium for which is predicted that 0.1% of all your microbes in your gut are E. coli, that particular E. coli. So even there's another estimate of a fraction. Yeast, another little fungus, roughly 500 genes. We already know 22% are enzymes. It's used for brewing the beer. Arabidopsis is a little weed, a little plant. We have about 1% of these proteins are known to be enzymes. Mouse, 7%, and human, 12%. Is that correct? 13% in human. So we now know there's 20,000 genes in human, and of those, 2,600 are already known to be enzymes. So how do we estimate those enzymes? And my first thought was, well, of course, we can use methodology, but we can also ask experts, see what they think. And then later, we can compare whether they were right or wrong. So here's my neighbor, next-door neighbor, Charles Dan, who is also in chemistry. And so I sent him an email, and he replies and says, well, E. coli, 30%, 35. Yeast, 45. Arabidopsis, 40. And mouse and human, 25. He has actually reasoning behind that. I will show you his email next slide. Then I contact another biologist, Thule from biology, and she says, I have no idea. I think it's 85% across the board. So I write 85% to everybody. And then finally, I ask my next-door neighbor at work, Eugen, what she thought. After all her degrees in computational biology, she knows something about it. And she predicts 40% for E. coli and yeast and 30% for the rest. And I have no idea which one is true. Matt, maybe can we ask you? What do you think? I don't know. Probably not. Anyway, so that's the motivation for this talk. So I think this is an interesting problem. You can see these problems everywhere where we would like to estimate these fractions. I think it's also obvious that we need certain rigor when we try to make these estimations. We need algorithms to estimate that because current algorithms are flawed in one way or another. And finally, we would also benefit by more precisely communicating both between scientists and particularly with the general public. So I think when we estimate things that there's 40,000 human genes, it's not a big deal that we missed, but we missed by a lot. And in fact, in the beginning, we thought there were 100,000 human genes. All right, so we make these incorrect estimates literally all the time. So let's see how we can set this up as a problem. And I'd like to introduce some notation. I'm going to get into a little bit more technical part of this talk to try to convey to you how we want to reason about these problems. And so I'm first going to introduce supervised learning in general, then semi-supervised learning, and then unsupervised learning. And then I'd like to show you that all of that is kind of the same thing, and how we can estimate these fractions and proportions properly in all these settings. So I'll show you some algorithms. For some of this problem has been solved. For some of it, it's not solved. It's still open. So in a supervised setting, we have, and we are going to disentangle the positives and negatives. We have a sample, x0 of negatives, which comes from some distribution. Let's call it p0 of x, which is probability of distribution of some feature, given that the class is 0. And you can imagine feature being, let's say, blood pressure. Okay, so one-dimensional, very simple, blood pressure. And 0 means that these are people who have no heart problems. And then you can think of the other distribution as a distribution of blood pressure over people who have heart problems. Okay, so very simple. So there's these distributions overlap. You can have a person maybe here who has heart problems but without high blood pressure, so these things overlap. So we have uncertainty. We have these two distributions. The whole goal of this supervised learning is somehow to understand how that x, blood pressure, relates to y, how it can predict this blood pressure. Not blood pressure, how it can predict whether the person has heart problems. And that predictor is a simple function, so let's call it y hat, which says that if x is greater than some threshold t, let's say this is a threshold t, then yes, heart problems, and if it's lower than threshold t, then no. And in this particular case, I'm assuming that these are equally likely, that roughly half, that I have equally large samples, and then 50% of my data set contains positives, those people with high blood pressure, and 50% contains people that are healthy, or at least not have no heart disease. But that's not enough, of course. That's too simple a function. We want to make it more complicated. We, in fact, want to predict posterior distribution. So we would like to understand the probability of blood pressure being 0 or 1, not blood pressure, I still talk about the same thing, probability of heart disease being no or yes, given blood pressure, So we can express this as a simple formula, as a joint probability divided by a marginal p of x. And because p of x is always the same, we can, at least when x is given here, so we can express it in this way. So this is the kind of probability of this data point given that disease is yes or no, times the probability of that disease, fraction overall. So already here we see that that is the class prior, that is the fraction of these people. So we can already see that we can't even make that prediction properly, probability that you or person has a disease or not, unless we knew in the beginning what those class priors were. Okay, so this is where this POI. And this is a constant factor. We can miss that class prior by a number, and then we will be by some sort of constant fraction away from the estimating true probability. This is called the posterior probability. So if you took machine learning from me, we did it all the time in that class, I think, or most of the time. So in the end, there is some natural distribution that is unknown for us because we only have positives and negatives in our sample. And in that distribution, let's call it P of X, because fraction of people with heart problems is actually smaller than people without heart problems. And I generated this distribution that only quarter of people have heart problems. So in that case, because of this class prior, we have to compare the values of these two distributions multiplied by a class prior. So the threshold might move over there a little bit if we want to minimize the error of prediction of people. Okay, so that is the problem that we have. The next problem that we have is a semi-supervised scenario. Note that here, I am assuming, I think that you guys, most of you know all of that, but I think it's good to go through these slides just either in the form of a lecture or just that we know the notation before we get into the algorithms. So here we have sample of negatives, we have sample of positives. These are the red and the blue bell-shaped curves. And we have a sample for data that we don't know any answer. It's just measuring randomly blood pressure on the street without asking people about their disease. And here we do know for some subpopulation of those that they have disease. And I am assuming that all of these data, X0, X1, and are coming really as IID samples from a distribution. So we have no problems with any sort of sampling with memory, or it's simply IID. Okay? So we just collect these people. And so that distribution P of X is, of course, a mixture of these positives and negatives. And I'm just re-expressing this as alpha times P1. So there's alpha is our parameter that we are really trying to find, the fraction of positives. No. The fraction of positives times the so-called class conditional distribution, and then the fraction of negatives times the probability of X given that Y equals 0. Okay? So that would be a kind of semi-supervised scenario when we have, this is a traditional semi-supervised scenario where we have both X0 and X1 and another sample of everything. The next scenario is the one we are mostly interested in. This is kind of slightly non-traditional semi-supervised scenario where we have only the positive sample. Those are the people, let's say, with heart disease. And then we have only a sample of random population. So we have no people without heart disease. Or we have proteins with known function. And then for the rest of the proteins, we don't know anything about their function, right? So those would be the unlabeled examples. And if you see these curves, so we don't know P0. We only have the mixture sample, the yellowish mixture distribution, and we have P1. Okay? So now our goal will be, again, to estimate whatever we can to find the best predictor. And then the third scenario, or the fourth scenario, and the last scenario here is when we have unsupervised learning problems. So we don't know either of the two. We only have a general distribution of people. We still might be interested to know who has heart disease or not. But obviously, this is a much harder learning problem. So we have that one sample of a mixture. And we are looking to recover these blue and red distributions, or parameters of these distributions. Anyway, we like to find that. And then if we can find all of that, we would like to find alpha. So what is the fraction of folks with heart disease in the general population? OK, so these are the problems. And some of these problems have solutions, as I said in the beginning, that are solved. By the way, please feel free to interrupt me, because if there are any questions, it's better to discuss it. OK? Maybe there is a little bit of notation here that might be confusing, so I'll try to. It's going to get worse, actually, in the next couple of slides before it gets better after that. So, OK, we want to find the probability that Y equals 1, probability that a person has a heart disease, or that protein is an enzyme. And we know how to do that mathematically. We just have to integrate over X. That is an easy thing to do. So our goal is simply to make a predictor of posterior probability that estimate that, if we know how, apply it on the sample of unlabeled data, and integrate empirically by finding an average over all data points. And that would be our estimation of the class prior. Okay, so if we could develop a predictor that outputs a posterior probability that somebody has heart disease, then we know how to estimate class prior. But obviously, we need class prior to estimate this probability, and we need this probability to estimate this probability to find the class prior. So we have, in general, a problem how to do that. If somebody gives us a pure random sample of the, or IID sample of the entire data, class prior is a trivial problem. It's just fraction of positives in your data set divided by the total size of labeled data points. So it's easy. But if you have a, let's say, balanced sample, you have equal number of positives and negatives, then actually you don't have the class prior. Your predictor will not be outputting the posterior. And in general, if you want to estimate something like the class prior, you're going to be off by a lot, depending on what is the difference in balance. And sometimes we are really interested in studying these rare problems, so you might be off by a lot. The simple idea is if you have a balanced predictor, you're kind of expecting to predict something not so far from balanced. So if you have only 1% of people with heart disease, you might overshoot in that predictor, right? So we need to kind of recalibrate these predictions to be able to estimate. And I should also mention, if your goal is just to rank data points, say Google want to give you a ranked list, then none of this really matters, because we can make good rankers solely from positives and negatives. We don't really need to recalibrate that. So depending on the problem you have, in our case, we are interested in actually estimating these things, but if you're interested in ranking, I don't think you need this. Okay, so let me guide you through the first method, how this can be done. So I'm going to go through several steps. I think it's an interesting method. So let's see how it goes. And if this is not a good kind of place to discuss that method in that detail, we can skip it. So first idea is let's think that we have the negative sample, we have the positive sample, and we have the unlabeled sample. So we have everything. It's not yet our real situation, positive and unlabeled. We have positives, negatives, and unlabeled data. So kind of classical semi-supervised scenario. So the idea is the following. Develop a classifier on labeled data. Let's call it FL of X. So you have positives and negatives. Let's say balanced sample. Okay? Estimate the accuracy of this classifier through cross-validation, perhaps, and get your confusion matrix. Here I'm just going to write this confusion matrix not as numbers, but I'm going to write it as fractions. So this is probability, the first number, that your prediction is 0 and that the truth is 0, right? So instead of calling it true negatives, we're just going to say immediately we're going to scale it, make it a kind of conditional probability. And this is obviously the fraction of true positives. The prediction is 1 given that the true class is 1. Okay, so that's your confusion matrix that we study in all these approaches. We apply that predictor to our sample, unlabeled sample X. And then we can observe the following. We can actually calculate the fractions of positives and negatives in that unlabeled sample, right? These are our predictions of positives and negatives. So you make your predictor. You observe the numbers of positives and negatives in there. And let's call them Q, Q0 and Q1. So let's say you have 50% positives, 50% negatives. Presumably, because your original predictor was 50-50, your Qs are 50-50 too. But then we should observe the following, that actually class proportions are P0 and P1, and that you can get Qs by multiplying this matrix by that matrix. So you can see that the probability that you predicted negative, given that it was a negative, times the probability it was negative, so that would be coming from P, times probability that it's prediction is 0, given that the true class was 1, times the probability that true class is 1. So it's a matrix computation. So from here, it's extremely simple to get estimation of class priors as inversion of this matrix P, the confusion matrix, times the vector Q. Okay, so you can think of this as a solved problem. If you have positives, if you have negatives, you apply them, you invert it, and you're done. So sometimes there are a little tricky parts here because estimating these numbers is not exactly as estimating the inverse. It's a nonlinear transformation. Yes?
So does it assume that F1 overfits on the label data?
F1 does not overfit. We are assuming that predictor is just done well. That you estimated properly. Even if it overfits, you estimated its accuracy correctly.
Because if it overfits, I can see this. You can probably bound the error with respect to the training set, right? If it doesn't overfit, then your estimation of P might be way off.
It might be way off, but if I have a good procedure to estimate P any way I know, let's say that cross-validation, if you have, let's say you have enough data. In that case, it's pretty simple, and if the sample is IID, obviously, so everything would work fine. But I could imagine having, I don't know how exactly it would look if a predictor would be overfitting, but I assume in our evaluation, the confusion matrix would show that, and it still would work, at least in theory. Actually, maybe it should be applied and seen, what happens. But you can then bootstrap this and kind of estimate this P, inverse P a little bit better because of nonlinearity. Expectation of something is not the same as that function of the expectation because if it's nonlinear. Roughly at the same time, there was a paper, this was first paper from ECML 2001, and then at the same time at ICML that same year, there's a paper for the same thing, estimation of class priors, but completely different algorithm. And those are the only two, actually, I think we know about. So here's the second algorithm. Develop that classifier, labeled classifier FL, from positives and negatives. And now we start kind of EM type of procedure. So we're going to say, well, let's calculate the class priors in the labeled data. So this is the fraction of positives divided by the size of the total data set. So positive size of the positive sample divided by the size of all your labeled data. And now we can say, well, okay, let's just say that that's my initial estimate of the actual class prior in the yellow distribution, in the sample X. And then I can iterate 2 steps. And I don't want to guide you too much to the formula, but you don't need to retrain the classifier. You only need to rescale its output by the fraction of your current class prior and the one on the labeled data. So you can see that I showed you at the beginning that the difference between class prior posterior is really by a constant off, right? That was that P of y in that formula kind of way back. So now we're just rescaling it, and as we update our estimate of class prior, we keep rescaling it. And then we estimate alpha always the same way. We apply that predictor, P that y equals 1, on the unlabeled data and just recalculate. And then, again, update this fraction, recalculate, and it converges. And when that method was proposed, it was the authors actually did not realize exactly what they were doing. They said it might get stuck in a local optimum. Now it's been shown just in a paper a couple of years ago, 2 years ago, 2.5 years ago, actually 2012, that there is a global minimum or maximum, and it's a convex problem in general. So there's a different type of solution that can be applied. So we know that this works. So I really consider this problem to be solved. If you have IID samples, there's really perhaps not much to be done. And before going to our real problem, let me just tell you what happens in unsupervised problem. We have an EM algorithm, which was proposed a long time ago. And here's, let's assume that these distributions P0 and P1 are Gaussians, and they're now I use dashed line again for that situation. And so we're going to iterate 2 steps. first step is given the current parameters, and if these are Gaussians, those are 2 means and 2 standard deviations. This is still all one-dimensional. Of course, it can be generalized. So given the current parameters, and the mixtures obviously are in the data, find probability that any data point in this sample X belongs to class 0 or 1. Somehow, based on initial sample, we can calculate that. Once we have that probability, that's that posterior probability we've been talking about all the time. Then we update the parameters. And in EM algorithm, I'll flash this one formula just to show you. If you estimate the mean, it's just the average of all data points. But in EM algorithm, it's actually weighted by the probability, mean of distribution, let's say 0 and then 1. You weight it by the probability that data point is in that group, and you divide by sum over all data points. It's a weighted average, really. Sigma can be estimated also trivially, and then we update our alpha again in the same way as always. Alpha is always...
The algorithm is not, in some ways, even an algorithm, because you have to derive it for a particular distribution. So if I tell you have Gaussians, then this is the EM algorithm. If I have other distributions, then you'll derive that EM algorithm for that distribution. So it's all kind of the same pattern. There's only one problem when we have these unsupervised approaches, and this is the problem of identifiability. That means that the solution is not necessarily unique when you have mixtures of distributions. So I can have distribution P of X to be the thing I want, alpha times P of 1 plus 1 minus alpha times P naught. But there can be another solution, beta times some Q, 1 plus 1 minus beta times Q naught. And those might give the same distribution in the end. So that's been worked out in the 60s, and there's a lot of knowledge about this. Okay. So the first approach towards positive and unlabeled data then might be just to work it out through the EM algorithm. So I can estimate the distribution of positive data, and then I can work out my parameter updates. I can make it parametric. For example, one way to modify the EM algorithm is estimate the positives separately and never again touch them. Only update the negatives, the mu naught and sigma naught, right, and alpha. So that would be perfect. But there's another approach where you can kind of write this joint likelihood function, and you can update these update rules. For example, mu naught would be the same as before, and mu 1 would be updated by the positive sample. If you derive it, okay, if you go through the process of derivation, this is how it would look. And so you can simply update the EM algorithm and solve this parametrically. And then you have your posterior distributions, and again, the same thing, and you get alpha. So you estimate the class prior again in the same way. And I'd just like to show you how it works, because I think that's interesting. I ran one simulation, not simulation, but for example, you generate 1,000 points in X1 from Gaussian distribution with mean 2 and standard deviation 1. Either 1,000 or 100 points. And then distribution X is 10,000 points from a mixture of normal 0, 1, which would be negatives, and normal 2, 1, which would be positives. And if you apply EM algorithm, in theory, it should find this 5%. Okay, here true alpha was 0.05, so 5% positives, everything else negatives. EM algorithm does not find it, and actually, if you run it for a really long time, it doesn't find it still. Here, I let it go for almost, actually, the threshold was 5,000 steps, and it won't find it. Even though theoretically it should find the proper distribution. But then if I say, okay, this is EM algorithm with one known distribution, so I tell it, F1, P1 distribution is normal with mean 2 and standard deviation 1. It finds it in 61 steps. So everything was done 50 times, and then I would record here what would be different estimation of the class price. So you can also estimate distribution 1 separately, and then never update it. So this is if you have 1,000 points, this is if you have 100 points. It works really well both ways. And then you can estimate the jointly, that was that formula I just showed you before, works actually a little bit better. And there are other cases that I'm not showing you here that you can see that it finds a kind of a better solution in terms of likelihood that you can actually calculate. Although it takes more steps. So okay, we know also how to update the EM algorithm, and if we want to translate our solutions to a parametric case, it's really no big deal. One problem with the EM algorithm is, though, that you don't really know how good your solution is. You might arrive at something, and occasionally EM will get stuck with close to 30%, but it should be 5%. So it has particular problems finding those low probabilities or very high probabilities. That is a big problem, and those are actually also the cases we are most interested in, when something is low or high. And that brings us to our non-parametric case. So this is, for this theorem, I of course will not go into the theorem, but this was Shantanu's theorem, where, well, actually other people, I think Marta has part of the theorem. I think, the fourth claim. Yeah, well, you added it.
It's mostly Shantanu.
Yeah, it was mostly Shantanu's theorem. The question is the following. So, okay, we now know how to solve it in a parametric situation. What happens if there's non-parametric case? Can we solve it? And is it identifiable? Is the solution unique or it's not unique? So I think it's obvious it's not unique, right? Because now P naught can contain P1. Right? Part of P naught might be also kind of P1. P naught can be itself a mixture containing P1. So clearly, and then there could be a different fraction of P1 in that distribution P naught. So clearly, this should not be identifiable. So there's no unique solution. But still the question is, can that be proven? What can be said about that? So the first claim is the family of distributions, where one is P1 and the rest is everything but P1, is not identifiable. I don't think anybody is surprised by this. But then the second question is, well, if we update that family of distributions, and say from all possible distributions but P1, remove that family where P naught contains a part of P1. So we remove all of those from that family. Well, that one is identifiable. And Shantanu is going to talk in this seminar next week, so he will give you more details on these particular claims. So we can identify a unique solution in that case. The next claim to me is maybe even the most important. Okay, these first two claims we later learned were also proved in 2010 in the JMLR paper. So even though I believe our proof is simpler and nicer, it's been done before, only a few years before. Now this claim is completely novel. The true alpha lies in an interval between 0 and some alpha star. And the overestimate alpha star of that alpha is smoothly related to the proportion of P naught, this red distribution in P1. So if you have a lot of P naught and P1, and if P naught is itself a distributed mixture, then you will overestimate by a lot. But if P1 is completely separate, then it will become identifiable and then there will not be overestimated. That suggests, because there is that interval, that suggests that there's a range of solutions that are equally good. And this is a key curve, key plot. And that range of distribution says that all alpha from 0, that's the claim of the theorem that we call this dimension group, that all of these are equally good. And that later, if there is some likelihood function, that likelihood should be great. That will be the key to our algorithm. So can we calculate some sort of likelihood function over the entire range of alphas, let's say using a grid search, 0.01, 0.02, and so on, to 1. There's only, say, 100 points. And in that grid search, we would then, if the theory is right, we would observe this type of shape, and then we would just multiply this point, which we know is identified. And that brings us to the algorithm, and then later results. So I'm going to mostly skip the details, but here's the idea. The idea is you can express any distribution. I'm just going to use P, which is a mixture. That's the yellow one, as the most slide. As a linear combination of some kernel functions.
Yeah.
Okay, and there is a coefficients or lambdas. So it's just this k-basis functions or maybe a kernel density functions. And from there, you can use a little trick and reparameterize our distributions P1 and P0. So the idea for that is that if we use these kernels to express P's, we can just rescale them, have a different weighted combination to express other distributions, H1 and H0, which would be P1 and P1. And then, so these new parameters, betas, are introduced here. So to P1, and then when you subtract this one from that one, you get H0. Again, I'm just going to rush through this. And then you can express your PRX. It has this form. Suddenly, when you reparameterize H1, H2 is calculated, you get this form. Of course, this beta alpha I, lambda I would cancel this. So it's the same distribution here, it's just expressed differently. But now we have a new set of coefficients beta. And note that this is so interesting that because the linear combination of betas and lambdas become our alpha, become our class prior, okay, in this formulation. So we now only have to find lambdas and betas and do this linear, of course, kernels, we have to figure those out. And then if we can express that, we can learn that actually not alpha, but alpha star, okay, that alpha at the end of that level function. So there's a couple of tricks to do that, and one way is to exclude, so because these would cancel these betas, we're going to estimate this separately from beta, this distribution. We're just going to replace it by P1 hat. That means just estimate P1 using some kernel density or weighted basis functions, and then plug that in, and then when we plug that number in here, this will become some H function. Okay? And then we can express likelihood over sample x1 and over sample x, and speaking that sum these two likelihoods, much like in that EM algorithm where we added component of sample x1 to the overall sample that I showed you in red. So this is kind of the same idea. You add these two likelihoods, but now we have parameters beta. Now we just need to find this. And the way we do this is we calculate this likelihood over all linear combinations of beta and lambdas. And then we design a little algorithm that finds this point that we call inflection point in our internal jargon. And that is our estimate of alpha. So let me show you how this works. That's the algorithm. So in the first example, we have either 100 or 1,000 or 100 points generated from that normal distribution, 2 and 1. And then 10,000 points are from the unlabeled data set. And this is our algorithm. First box plot is with 1,000 points, and the second box plot is with 100 points. The second two are our competitors that I completely skipped in this case. It's Elkan and Nota published a paper in 2008. It will take a bit of time to go through this algorithm, and the algorithm has also an error, and a big one. So it is going to overestimate your alpha all the time. It has a theoretical error in the whole formula that is used to calculate. And then we have an EM algorithm here run with different set of steps. And I used 5,000, and that takes a long time. I think Shantanu here used a smaller number of steps. How many? Yes.
I was just curious, what's the vertical axis?
Vertical axis is the class prior. Thank you for the question. And this dashed black line means that's the truth.
Oh, okay.
The data was generated with this truth, and we run 3 different algorithms with different sizes of data sets. So first is our algorithm with 1,000 data points, our algorithm with 100 data points and positives, and always 10,000 unlabeled. Elkanota with 1,000 and 100, and then general EM algorithm, just 1, with a little catch that at the end, we assign the mean to be the class 1 that's closer to the mean of positive sample, because otherwise they can flip. So But if you run it with with only a few hundred steps, it's going to find something that's close to 0.5. It's not going to be a good solution. And these are our likelihood curves. But the black line, again, is the truth. That's what we would like to find. And the red line is what our algorithm identifies as this inflection point. And here, because it's only 5% of the true class prior, it kind of immediately goes down. So, and you can see how this works in practice. Here's another data set. Here we use Laplace as a true distribution. So here, Gaussian EM algorithm is kind of working outside of the assumptions. And we are still not sure why it missed by so much over there, the EM algorithm. It just finds the opposite solution somehow. That could be a bug. We are looking into that, but it seems like there's no bug. So we kind of overshoot a little bit. 0.25 is the correct. We find 0.3. L cannot overshoot by more. And then if you see the likelihood curves, this is the truth. Our algorithm finds this. Now, I would like to point out here that personally, we don't even need an algorithm to find an inflection points. In reality, when you want to estimate class prior, you have only one data set. You can't repeat it here 50 times. So this is repeated 50 times, and this is one of those 50 likelihood curves. In the end, you would only have one likelihood curve. You can eyeball it. If you're a data analyst, you can really say here, well, I think I would probably eyeball closer to the truth here than the algorithm did here. And now the question is, can you apply this to multidimensional data? After all, we've been talking about distributions and estimating distribution that cannot work on large sample, large dimensionalities of data. Well, here's a trick that can be applied. We train a predictor between positives and unlabeled data and apply that predictor to unlabeled, to both of these samples, to get new distributions of scores of that predictor. We'll call them Q, Q1 and Q. And Shantanu will discuss this. Well, that transformation preserves our class prior. And we can just use our one-dimensional algorithm to address this. So we train a predictor, we use the score distributions, we estimate class prior. How does that work? Here's another synthetic data set. We use waveform from Ryman. We are somewhere, again, 1,000 and 100 points. 0.5 is the truth here. L cannot overshoots. EM algorithm does well. It usually does well when it's around 0.5. Was there a question? No, okay. It usually does well, and this is the likelihood curve. You can see it looks very nice, actually. You can eyeball it, or you can develop a little algorithm that identifies that inflection point. In our case, we look at the slope before and slope after and find the point of the biggest change of slope. Right. This is a ball in the box problem. We generate a 10-dimensional sphere. Inside are positives, outside are negatives. Here, 0.75 is the truth. This is our performance. L Canoto, again, overshoots. Well, EM does really well here because ball in the box is spherical. It really handles those types of data points, data sets well. And again, like, yes?
You're estimating alpha star, right?
Yeah.
So that means that even with 1,000 data points, you don't include the real value.
No, the actual real value is 0.75, right. But alpha star that we are estimating is going to be pretty good. So if these...
But the estimate there is like 0.73 or something, right? So well, it should lie between 0 and 0.73.
Say it again?
Or isn't your theorem that the true value has to lie between...
True value should lie between 0 and alpha star.
But here your alpha star is lower than the true value.
Well, it doesn't always work well. Okay, so you have a script that should estimate the slope, right? So this is automatic determination of the slope. So it can go slightly below. But generally, it should overestimate. If you have a distribution, so obviously it's a non-identifiable problem, so it should, in principle, but it does happen.
And you want it to be overestimated if you want to make sure you include the real value.
Yeah, but you don't want it to go too far off in any direction, right? So So the question is, again, is this good or not, right? I think it's good, but yes, it kind of defies theory a little bit. And then if you want to look at the table, so if we use normal distribution with separation of 2, we actually can beat EM algorithm and canonical. These numbers here are the mean absolute error from the true alpha, the way we generate the data. If the separations is very large, then you cannot beat EM algorithm, because these are generated as Gaussian. So EM is just going to find it no matter what, and it beats you. Then with Laplace, we again win with low separation, but lose on high separation. And then these are these other data sets. Sometimes you can do mixed bag. Now, a couple of real-life data sets. These are from UCI Machine Learning Repository. Here, this is a bank data set. True value is about 0.1. We find about 0.2. Alkan finds about 0.3 something. EM algorithm is somewhere else. So we all miss. 10-digit data set, the truth is 0.23. We find 0.25. Alkan is maybe a little up. EM algorithm is even more up. In this case, the likelihood curve looks kind of beautiful. It has this sharp decrease, so it means that the distributions are relatively well separated. So the alpha star is actually alpha in this case. And then you can apply to other data sets. And if you look at all these data sets, we had 10, so 8 are here and 2 I showed you just before. You will see that the results are not too bad. For example, if you look at this concrete data set, we are hitting the right values, but so does EM algorithm, but with smaller variance. So if your data set is kind of according to the assumptions of the EM algorithm will beat you. So here it has lower variance. So it's, if I show you the table on the concrete data set, it will beat us, but it will lose some all other data sets. So there's the whole table of 10 data sets and all these 3 different algorithms. Now let's go back to enzymes so we can conclude this story. In enzymes we have proteins. We have to develop this predictor, and first we have to encode every protein, which is a sequence of 20 symbols. We will encode it into a sparse representation of k-mers, where every k-mer is, there's 20 symbols times to the 4. So this MEEP will be 1 here, and so on. This protein is actually not an enzyme. It's a tumor suppressor. So it should not be the enzyme set. So we developed just a regular support vector machine, linear kernel, Platts correction to get the posterior distribution on the labeled set, or the data set we use. It has good area under the curve, so the ranking works. The question is, what do we estimate? So here's some results. In yeast, we estimate 33% of enzymes. Alkan estimates 62%. So Charles 0.45, Eugene 0.4, Thule 0.85, and Matt. On E. coli, we think there's, okay, so this number, this is what we estimate. Here we really don't know the truth. Our algorithm will find this value. You can maybe eyeball it a little bit differently. The curves are smoother, so you can see that the distributions are overlapping. The separation between positives and negatives is not that great. And this value here is only on the unlabeled part of the data set. So we have to add these proteins that we already know are enzymes. So here you observe below 0.2, but actual number is 0.88, because already 22% are enzymes. So these are just the additional ones to give us 32. Anyway, E. coli, let's say maybe 50%, seems about right. And then we have Arabidopsis, our plant. We estimate 20%, and Charles agreed. Eugene is 30, and Thule is 85. And then human, these curves look fairly convincing to me. To me, that's a sign that probably there is something in this method. It appears that these numbers kind of look believable to me. And then in human, we have these the numbers we estimate 21%. So I showed these numbers to Eugene just earlier today, and she declared herself a winner. These 3. I think it seems about right. So she won in 3 out of 4 if you count. All right, so where are we now? I think I showed you, I hope, the importance of this problem. And some ways to solve it, but I don't think the story is finished. Many things remain to be done. And first thing is clearly what if X1 is biased sample? What should we do then? What if there is noise in X1? So what if the positives are not really always positives, but there's a fraction of them that are incorrectly labeled? That was all considered to be non-existent here. Who knows how that affects enzyme estimation, right? Because maybe some of these proteins that we think are enzymes are not, or they are biased in some way. Well, we spoke to Sriram a few times about moving this to the relational domain. So some of you might be looking for projects. I think that kind of that's what I'm talking about here, if you're interested in these types of things. So how to move this to relational data, we had some ideas how to do this. There's other things like that you might want to talk to Marta, kernel density estimation, and all these approaches. And finally, real-world applications. I'm particularly interested in bioinformatics data, but there's many other domains where you might be actually interested in estimating these fractions, and it can change the whole setup of the phenomenon that you're studying. So, and with that, I'm done, so thank you.